In the last lecture, we have discussed the low frequency small signal model and high frequency small signal model. So basically, low frequency model is help us to calculate the intrinsic gain of the transistor, and high frequency model help us to calculate the intrinsic speed of the transistor. So, what is the intrinsic gain and what is the intrinsic speed? Later on, we discuss in this lecture. And these are the two analog figure of merit. So we have to trade off between these two things. Intrinsic gain, if we want to increase the intrinsic gain, so we have to compromise the intrinsic speed, and if we increase the intrinsic speed of the transistors, so we have to compromise the intrinsic gain. So these are the two trade-offs. So in fact, intrinsic gain is a small signal voltage gain transistor can provide at low frequency. So this can be achieved in the active region of the transistor, and in this region, we have the common source configuration, or the source is grounded. So input voltage is applied at the gate and source, at the gate, and the source is ground. So gate and source voltage and the output observed at the drain or at the drain and source. So we will see, in fact, is the value of V out by V in of the transistor. So in fact, VGS is equal to V in. So we substitute the value of V in is equal to GM V in, and the output is taken across the output resistance of the diode of the transistor. So this is, in fact, is GM VGS into RDS. So the input voltage is V in, and the output is GM VGS RDS. So GM V in RDS. So we have, in fact, the value of this is GM V in RDS divided by V in is equal to GM RDS. Sorry. So the value of GM is equal to 2 ID by VF, and RDS is equal to 1 by lambda ID. So intrinsic gain is 2 ID VF into 1 by lambda ID. So this ID cancels ID, and that is equal to 2 lambda VF. So intrinsic gain is, in fact, is equal to the 2 lambda VF. So in fact, small values of VF are used to maximize this gain, and this lambda is proportional to 1 over L. So in fact, if we increase the length, so we can increase this intrinsic gain. So by maximizing the gate length, we will increase the value of AI. So if we consider the unit frequency gain, so this is the maximum operating frequency at which the transistor provides the gain. So it is most common measure of transistor intrinsic speed. It is also measures in common source configuration. So here we have the CGS and CGD, and we have, in fact, calculate the value of this by a relationship Ft is equal to Gm by 2 pi CGS plus CGD. So this Gm is in fact is the resistance that is equal to 1 by 2 pi RC. So that is the unit frequency gain, and CGS is much greater than CGD. So we have the value of Ft is, we substitute the value of Gm and we substitute the value of CGS only. So this will give us the relationship 3 mu n Vf 4 pi L square. So in fact, here we, to increase the unit frequency gain, we have to maximize the value of Vf and we have to minimize the gate length. So that is reciprocal in case of the intrinsic gain. That is reciprocal in case of the intrinsic gain. So, so in fact, if we want to increase the intrinsic gain, so the Ft will be minimized. And if we want to increase the value of Ai, so Ft will be increased. So these are the two reciprocal terms which we commonly use as analog figure of merit for the transistor. Now there is a sub-threshold operation. So in fact, we have the weak inversion of the transistor when the value of Vf is less than 0. And we have the moderate inversion when the value of Vf is around 90 millivolt, and for Vf greater than 100 millivolt, so we have the strong inversion. And after this, we have the mobility degradation. So we have derived the value of transistor relationship in the strong inversion mode. So what about if the value of Vf is less than 0 and the transistor operates in weak inversion mode? So that relationship of ID sub-threshold is given by this relationship. So that is the exponential relationship. That exponential relationship is in fact is the power of QVF divided by NKT. So NKT by Q, the inverse of NKT by Q is in fact is the slope of the is the slope of the IDVGS curve, and that slope is in fact is a straight line, and that is in fact is also called the sub-threshold slope. So that value is 2 by 3 NKT by Q if we use the ID on, if we calculate the ID on logarithmic scale. So in short, we have the value of this N is multiplied by the value of the capacitance, and that power is 1.5, and ID naught is in fact is N minus 1 mu n Cux KT by Q square. So in fact, when the VDS when the VGS is equal to 0, or when the VGS is 0, so the value of ID is not equal to 0. So that is called the sub-threshold leakage current. So this value of when the transistor is off, even then there is a small leakage current, which is the source of power consumption, and that is entirely dependent on the temperature. So that we want to minimize this value of current. So this value of current can be given by this relationship. We can substitute the value of ID naught to get the complete equation. So now what will be the value of GM in subthreshold region? So we will have to take the derivative of this ID subthreshold with respect to VGS. And that value is in fact is ID naught W by L EQVF by NKT. So the derivative of this is in fact is the same exponential into the derivative of X, so which is Q by NKT into 1. So this is in fact is the ID subthreshold. So we have Q NKT into ID subthreshold. So this GM subthreshold is independent of the value of VF. So now we know this this is the GM in the strong inversion, and this GM is in the weak inversion or the subthreshold region. So in active mode, so we equate these two equations to find the value of VF. So this 2 NKT by Q is the point where we have the boundary for the weak inversion and strong inversion. Beyond this value of VF, we have the strong inversion, and at this value we have the up to this value of VF we have the weak inversion. So now we have the mobility degradation point. So mobility degradation is occurs when we have the large electric fields. So drain to source high voltage will cause the oscillation of the transistor up to the maximum velocity given by 10 raised to power 7 centimeter per second. So this is the velocity saturation point. So further increasing the value of the voltage will not increase the acceleration of the carriers. So vertical electric fields, in fact, will cause to decrease the effective channel length and will cause charge carrier collisions. So that value is 5 into 10 to the power 6 volt per meter. So this value of mobility degradation is in fact is mu and decreased by the component 1 plus theta VF power m into the whole of the power 1 by m. M and theta are device parameters. So now we will substitute the value of theta effective into this equation. So we will get this new value. So this for small VF, so this component, this entire component is equal to 1. And for VF much larger than value of theta, so this component is equal to 1 by theta VF. So this is equal to 1 by 2 mu n CUX W by L VF by theta. So For GM in the mobility degradation, we have to differentiate this with respect to VGS, and that is equal to 1 by 2 mu n CUX WL into 1 by theta. So relating this to the value of GM, so we have VF is equal to 1 by 2 theta. So we have the strong inversion up to the value of 1 by 2 theta, and beyond 1 by 2 theta we have the mobility degradation. So we have seen this relationship ID versus VGS. So we have the subthreshold region up to the value of 2 nkt by q, and we have 1 by 2 theta. After that the mobility degradation will start, and the GM is with respect to VGS is Q ID N KT and mu n COX W by L VF, and that is equal to 1 by 2 mu n COX W by L 1 by theta. So here, if you compare these three regions, with subthreshold region, the strong inversion, or the active region, and the mobility degradation region. So subthreshold, active region, and mobility degradation region. So you have seen that what value of VF is required for the transistor to operate in these regions. But the value of GM is in fact linear in the active region, and that is also the behavior of ID is linear in this region. So usually the analog design is performed in the active region. So mostly we design an analog circuit in this region. For subthreshold regions, we have low speeds and low power consumption, and in mobility degradation we have high speed operation, and we have minimum parasitic capacitance, minimum aspect ratio, and we have used this region for high speed operation. So this is all about chapter number 1, and we finish this lecture here, and in the next lecture we will start studying different basic components which we can design in the active region, or we can design circuits using the low frequency or high frequency small signal model of the transistor in the active region. So we will begin it from the next lecture. Thank you very much.